Hi Bobcats! The good news, this is our last video for chapter 11, which is our last chapter in Chem 1341. Woohoo! We are going to look at applying molecular orbital theory for some a little bit more complicated molecules. We're going to generate these MO energy level diagrams for the second row homonuclear diatomic molecules. So those are on the ones on the second row of the table. And again, some of them form and some of them don't, just like what we saw with hydrogen and helium. And we're going to just continue using our basic ideas from way back in that chapter on quantum, where the Aufbau principle says we put electrons into the lowest energy orbital that's available first. The Pauli exclusion principle, which tells us we can put at most 2 electrons in any one orbital. And then Hund's rule, which tells us if we have a degenerate set of orbitals or a set of orbitals that all have the same energy, we're going to fill electrons singly first and then only pair them up when there aren't any unoccupied orbitals left at that same energy level. And then we're just going to look at some kind of cool diagrams of some of the most bonding MOs for some more complicated molecules. The energy level diagram for the second row homonuclear diatomic molecules actually shifts halfway through the second row. For the elements boron through nitrogen, we're going to use the arrangement of orbitals that's on the left-hand side of this diagram. And then for the elements oxygen through neon, we're going to use the MO diagram that's on the right. And the part that's highlighted in orange is the part that shifts as we move deeper to the right in the periodic table. You can see the bottom part of this looks very much like the first row energy level diagram. We take the s orbitals and then we hybridize them and we get the sigma and the sigma star orbitals. When we hybridize the p's, we're going to get both sigma and pi orbitals. Then of course we get both the bonding and the anti-bonding orbitals. And then again, yeah, this orange part just shows that as we move further to the right across the periodic table, the order of those bonding molecular orbitals formed from the p orbitals shifts a little bit. Just real quick to demonstrate something, why don't we take N2 nitrogen and fill its MO diagrams. Let me go with a green paint. Nitrogen is going to have 5 valence electrons because it's in group 15. So if we have a molecule of N2, we're going to have 2 times 5, which is 10 electrons. So if we go to put the 10 electrons into this MO diagram, we'll start with the lowest energy one. There's 1, 2. After we have 2 electrons, we can't put any more, so we have to go to the next energy level, which will be the sigma star. So there's the 3 and 4. Then electrons 5 and 6 should go in singly by Hund's rule, and then 7 and 8 we're forced to pair them up before we jump to the next energy level where we replace 9 and 10. To contrast that, let's do oxygen over on this other side. Oxygen's in group 16, so it's going to have 6 valence electrons. 2 times 6 is 12 for the 2 atoms, so we have to put 12 electrons into here. So starting way down at the bottom, we'll put in 1, 2, and then moving up to the next orbital, 3, 4. The next orbital, 5, 6, and then the next set's degenerate, so we have to put them in singly first. That's 7 and 8. Then we can pair them up, 9 and 10, and then we still have 2 more to go. When we hit this pi star, they are degenerate, so electrons 11 and 12 should go in separately. This is important because in a little bit I'm going to ask you to go and watch a video And in that video, they demonstrate that nitrogen is something called diamagnetic, and oxygen is something called paramagnetic. And we can actually see the origin of that right here on these energy level diagrams. If something is diamagnetic, all of its electrons are paired up. So all electrons are paired. And so if you look at this energy level diagram, anywhere an electron is drawn, it is paired. There's one up and one down. But to be paramagnetic, you have to have one or more unpaired electrons. So yeah, paramagnetic means one or more unpaired electrons. And we'll see in this particular example, oxygen has 2 unpaired electrons, making it paramagnetic. Now, something that is diamagnetic is very weakly repelled from a magnetic field, whereas something that's paramagnetic is attracted to a magnetic field. Now, these are both weak effects, but paramagnetism is quite a bit stronger than diamagnetism. Diamagnetism is really, really hard to observe. Basically, things that are diamagnetic look like they don't really interact with a magnetic field. Things that are paramagnetic tend to show just a little bit of attraction for that field. So I'm going to ask you to watch a video in a little bit that's based on the fact that nitrogen is diamagnetic and oxygen's para. All right, this complicated looking diagram is just showing the electrons for all of these molecules arranged into the appropriate orbitals. Oh, excuse me, it's getting up past my bedtime. B2 is in this first column, then C2 for carbon, then nitrogen, N2 like we did on the last slide, oxygen like we also did on the last slide, and then fluorine and neon. And I think if you look at the bond order over here for Ne2, you're going to discover, let's see, I lost my pen, there it is. The bond order for neon, Ne2, is going to be 1/2 the number of electrons that are in bonding orbitals, which are the ones without the asterisk. So for bonding orbitals, we're going to have, I'm going to mark those with a little side arrow. That's bonding. This one is bonding, and this one is bonding, and then these other ones are anti-bonding, which I'll just use the standard asterisk for. So our number of bonding electrons are 2, 4, 6, 8. So we have 8 bonding electrons, and then our number of anti-bonding electrons, 2, 4, 6, 8 as well. So once again, we end up with a bond order of 0 for neon, which is what you would expect. You would not expect a bond to form between 2 neon atoms. Take a moment and calculate the bond order for nitrogen, and calculate the bond order for oxygen and also for fluorine, and see if that matches up with the Lewis dot structures that you could draw for nitrogen, oxygen, and fluorine. I think you'll find it does. So yeah, I did want to just put into words the deal with magnetism. Diamagnetism and paramagnetism are very weak effects that are due to the way electrons interact with a magnetic field. The diamagnetism is observed in substances where all of their electrons are paired up, and it's a very, very weak effect. So, again, sorry. Things that are diamagnetic, for the most part, look like they just don't interact with the magnetic field at all. But something that's paramagnetic is weakly attracted. And while it is a weak effect, it's quite a bit stronger than diamagnetism. But both of those things are blown away by ferromagnetism, which is what you normally think of when you think about magnets, and you think like, you know, refrigerator magnets or those little neodymium magnets. And that's a very strong effect, and that has to do with large clusters of atoms that are referred to as domains lining up within the material, and it's a much, much stronger effect. All right, so here is the link to the video on this experimental demonstration of nitrogen being diamagnetic and oxygen being paramagnetic. Particularly the oxygen part, I think, is really a bizarre thing to watch. Before we conclude, I wanted to just kind of give you a taste of some of the molecular orbitals from some more complicated molecules. I'm going to start here with ozone, O3. We know we're going to need resonant or molecular orbital theory to describe the bonding in ozone because we have to draw resonance structures for it. There's no reason to favor putting the double bond on one side or the other. And so that's a pretty good idea that you're going to need molecular orbital theory for a good description. And the MO that I'm going to show you is just the lowest energy MO, and it is delocalized over the largest number of atoms. If we take that unhybridized p orbital on each of those oxygens, because notice each one of those oxygens is either unhybridized or sp2 hybridized, so they'll all have an unhybridized p orbital available, and the lowest energy molecular orbital has all of those p orbitals overlapping side by side to create this molecular orbital that runs across the entire molecule. Notice that the actual three-dimensional structure of this is not linear because that central oxygen atom is sp2, so it's going to have that 120-degree bond angle in there. And so in that lowest energy molecular orbital, the electrons are free to roam across all three of these atoms. The next molecule I want to take a look at is benzene, which hopefully you already went and peeked at the molecular orbitals for this. And I want to focus again just on that absolute lowest energy molecular orbital. It's going to involve all 6 carbon atoms that are in the ring of this benzene molecule. And each one of those carbons is sp2 hybridized, leaving an unhybridized p orbital available for bonding. And if all 6 carbon atoms are in a plane, then these 6 unhybridized p orbitals can line up side by side with each other and delocalize the electrons in a ring around the entire molecule. And that ring of electron density is both above and below the plane of the molecule. Since the p orbitals all have 2 lobes, we end up with 2 essentially donuts of electron density, one above the plane of the carbon atoms and one below. If you're drawing Lewis dot structures and you need to draw resonance structures, that's a pretty good indication that you're going to need molecular orbital theory, and you're going to end up with electrons that are delocalized over at least a portion of the molecule, if not the entire